Hello everyone. Now we are in the AE357 Petroleum technology, and we come to an important part of refinery, Chapter 4, Crude Oil Distillation. Let me refer to the entire refinery here that we used to mention earlier. In this chapter, we will focus on only the red cover this. A big yellow unit. Here is called CDU, standing for Crude Distillation Unit. Some textbooks may present in ADU, which stands for Atmospheric Distillation Unit. The product from this unit are as shown here. You can have light state run gas, light state run naphtha, heavy state run naphtha, kerosene, like gas oil, atmospheric gas oil, heavy atmospheric gas oil. And the yellow unit, the smaller one here, it represents vacuum distillation unit, or this vacuum fractionation. And of course, the product from this unit will be called as like vacuum gas oil, medium vacuum gas oil, and heavy vacuum gas oil. So you can notice that in terms of what they put atmospheric and vacuum, so you can notice where the products come from. And before we talk about atmospheric distillation unit, we should prepare the feed of the crude oil ready for the good operation in this unit. The required unit in front of ADU is the desalting unit here. And this slide showing the detail of the system. Many heat exchanger units are used to heat up the crude oil. Now you can see that there are several heat exchanger and heat exchanger trains before getting into passing this crude oil to distillation unit. Some heat was utilized from the heat recovery, from the condenser, or even from the pump around. This is the heat exchanger getting heat from pump around. We will talk about the pump around later in slide number 18. From this diagram, water will be added to the crude oil. After that, using the mixing valve to balance the flow and getting well mixed before feeding to the desalting unit or desalter. The feed should enter to the bottom. Actually, this is not the right diagram, but actually the feed should enter to the bottom of the vessel. Students may wonder why crude oil required to remove salt. In general, we classify the impurities in crude oil into two groups. The first one is things that insoluble in oil, or what we call oleophobics. And the other is things that soluble in oil, so we call it oleophilics. Let's focus on the salt. If salt concentration is too high and cannot be removed totally, the salt can cause many problems. Shows here, it can deposit on the surface of the steel tubes, which will decrease the heat exchanger coefficient or overall heat transfer coefficients, as you know, and can plug into the heat exchanger tubes that cause or creating that's causing or creating pressure drop along the line. And the last one, the salt here, base, chloride or choline, can poison the catalyst. What I mean, not only the catalyst upstream, but also the catalyst downstream, in downstream process. The salt content of the crude is reported in PTB, which is pounds per 1,000 barrels. Not very much, but the concentration can shoot up to about 2,000 ppb. This content has to be lowered down to 2 to 5 ppb eventually. Well, similar to water, typically the content of water is between 0.5 to 10% volume. But what we have to do in this desalting and dewatering is to lower down the concentration to 0.2% volume. The salt in the chloride from contains average about 75% in sodium and 15% in magnesium. And about 10% for calcium. Salt can hydrolyze to form hydrochloric acid or even in gas at high temperature. And HCl here, after exposed to water that's condensed in the crude tower overhead, can cause serious corrosion. The hydrolysis of calcium chloride and magnesium chloride here will take place at the temperature around 200 to 230 degrees Celsius here in this reaction, and about 120 degrees Celsius in this reaction respectively. Students have to write down by your own on the reaction of the hydrolysis of sodium chloride, which of course the reaction will take place at higher temperature, particularly higher than 500 degrees Celsius. Now we come to the removal unit. What we talking about, the desalting unit. There are actually 4 steps in the desalting unit. The first one is water washing. Well, water is mixed with the incoming crude oil through a mixing valve with special mechanic plug. In terms of reducing the cross-sectional area here, the well mixing coefficient will be increased. The static mixture is installed upstream in this site for the contact between the salt in the crude oil and injected wash water. Water will act to dissolve. Particularly here we have the solid particle, and now it will dissolve the salt content in the crude and mixing distribution in the salt into water, uniformly producing a very tiny droplet. Tiny droplet meaning in range of 1 to 10 micrometer in diameter. And not only that, we do have to add some chemicals here. What I mean is demulsifying agent to add and to aid the breaking of the emulsion by removing the photones from the surface of droplets. The second one, we finished the water washing, and the second step is the heating system. The heating steps. We have to put steam to heat up the system to 130 to 115 degrees Celsius. This will affect the water oil separation. Then we do have to work on the coalescence. With a tiny droplet of 1 to 10 micrometer, they cannot settle down. So what we have to do is to put the electric field between these two electrodes to ionize the water droplets that can attack to each other. You can see from this picture here by induced charge and electrostatic attraction. So when the size getting bigger, they will settle according to Stokes' law. Well, the desalting or the desalting unit or the desalter of this design can achieve almost 90% salt removal. However, we can put two stage desalting units in order to increase the removal efficiency up to 99%. For the crude free, after the crude free from the salt, it will come out from the desalting unit at about 150 degrees Celsius, where it will be heated up again to about 500 or to 400 degrees Celsius by the furnace. What I wrote here is 330 and 385 degrees Celsius. I presume that the temperature out of the furnace is about 400 degrees Celsius. To some plants, heat exchanger network may be used. We will visit on the heat utilization by pump around later on. The main column is typically 15 meter high and is equipped with valve tray or bubble cap trays. Some of them have 30 trays, some of them have 50 trays. In this figure showing here, I would like to show how big the ADU and the VDU are. This is also the size of ADU, and this is also the size of VDU. You can compare with the size of the truck here. And this slide shows insights on what kind of bubble cap trays is about. Well, liquid. Okay, liquid from the tray below. Was vaporized and passed to the hole. You can see this is the hole for the bubble cap and the vaporized products. The vaporized products will generate an equilibrium with the liquid on this tray. So the vaporized product will make the equilibrium on this tray for the better separation. And liquid from the liquid with heavier products okay, will in this above tray will overflow to the tray below for the further equilibrium. Alright, and this is the kind of bubble cap look like. And you can see what the overflow is to this side. Well, typical designs have the tray distribution between products as shown in this table. I mean, if you would like to have the kerosene and gasoline separate, well, you may need many trays for that. In general, we cannot. In general, we have cut points. And this is what you know from the first 3 chapters. We have the cut points for each product. However, chemicals in the crude is quite complicated. It's quite complicated. It is very difficult for the perfect cut. Just like you cannot make the product of gasoline in exactly 90 or 80 degrees Celsius to 10 degrees Celsius. Each product has to be analyzed for the volume percent vaporized again. See, in this case, it will look like the one in this figure here. You can see that there is an overlap. You can see the overlap. Okay. The more overlap the product is, the specification of the product is hard to meet standard. So what it means is the more overlap is low selectivity on the product, and we have to get into the acceptable overlap value as shown in this table. Well, when we talk about the gap means, what I mean is the difference between the temperature at 5 degrees of the heavier cut to the temperature of 95% of the light cut. So the gap is equal to temperature of heavy cut and light cut. If the number is in positive, it means we have the good fractionation system. Let's see how to calculate the gap of the kerosene and the gas oil. This is the kerosene, this is gas oil. Of course, kerosene is lighter than the gas oil. Okay. The red lines present 5% and 95% in volume. Then we find out that 5% of the heavy product, which is in the blue one here, represent the gas oil, and the 55% of the kerosene of the light product in the green one lie here. The difference is about -5. The absolute of the product is acceptable. The negative difference is called the overlap. What does it mean is some of the light product is still in the heavier product. For example, in general, the cut point in the crude distillation column are controlled by the overhead vapor temperature, and whenever we change or draw off rate or change the draw off rate of the product, it will affect to the cut point of heavier products below. For example, if I lower the kerosene flow rate, it will lower the end point, and that will affect the initial cut point of the light gas oil and heavy gas oil. For the degree of fractionations, this depends on 4 factors. The important 3 factors here. The first one is the vapor liquid flow rate in the column zone between 2 streams. What it means is we have to make the relationship of this, so this will prevent of the flooding in the trays and also the heat accumulations in the top tray zones. And also, if we have many trays in the column, it means we will have more equilibrium phase taking place, which means we will have more fractionation degree higher. And also we have to extract some heat out by the pump around as much as we can, otherwise the salt may accumulate at the top of the column. Well, after the crude be heated to some certain temperature, 400 degrees Celsius, of course this temperature some crude may partially vaporize and the crude will be fed into this area of the column, the flash zone. At this location, or called as the flash zone, the feed which is vaporized will be risen to the wash zone. This is to prevent the dry up at these trays. So we need some overflash value at this point. The overflash is the ratio of the volumetric flow rate of the liquid flowing from the tray above, the feed, and the feed. The value should set at about 3 to 5%. This is to guarantee that the plate between the flash zone and the first draw above it do not dry up. This will help to improve the quality of atmospheric heavy gas oil for the better equilibrium and good separation. Now come to the column pressure. The pressure inside the crude distillation column is controlled by the back pressure of the overheat reflux drum. For design, the overheat drum pressure is estimated first. So this is at the bubble point pressure of the top products at the minimum cooling water temperature, as we know. And then the flash zone here, the flash zone pressure here is equal to the overhead drum pressure plus the pressure drop in each tray summation. So in general, the back pressure is around 0.2 to 0.34 bar gauge. And then at the top tray here will be a little bit higher than the reflux drum, around 0.3 to 0.4 bar gauge. And the flash zone pressure here will be equal to at the top tray plus this number. So approximately we will have the pressure drop in each tray equal to 0.1 to 0.2 psi. How about the temperature at the overhead? The overhead temperature must be controlled to about 14 to 17 degrees Celsius higher than the dew point. This is to prevent the corrosion due to hydrogen chloride dissolved in the liquid water. I think you have to go back to the first slide about the salt dissolved, which has the hydrolysis at about 120 degrees Celsius for magnesium and allow 200 for the calcium chloride one. So we can set the temperature higher than that dew point a little bit, but not to that certain temperature we mentioned before. And this is some example. In case that the overhead stream contains 8.5 mole percent of water at the pressure of 34.7 psia. So calculate for the overhead pressure or overhead temperature for the safe operation. So what we have to do is find out for the saturated temperature at that pressure. So what we get is 2.36 bar. So we multiply with the water fraction in that stream and come out is about 0.2 bars. From the steam table, saturated steam temperature of 0.2 bar is equal to 61 degrees Celsius. So we add some 17 degrees Celsius there to that temperature of the dew point. So what we get is 78 degrees Celsius for the operating condition at the overhead. Well, let me go back to things before the crude distillation column a little bit. Before the crude coming to the furnace, you will see PA, which stands for pump around. Some plant they stand alone like this. Some plants they do in terms of heat exchanger trains. Or you will learn a bit more in pinch technology to utilize better energy consumption. Well, what they do is this. The pump around stream is a liquid stream withdraw at the point below a side stream tray that is cooled by the cold feed as part of preheat exchanger. Three purposes of the PA are here. The first one, as you can see from here, stream B, which is colder stream, condense more rising vapor and back to the tray above. This will help to increase the internal reflux. So then the liquid will be condensed more, and this will be also compensate the withdrawal of the product out in some certain tray here. The second one is to reduce the heat accumulation inside the stream, because we don't want to accumulate the heat inside the stream that much. In this case, we can remove the heat out by the from the column by using the pump around, and that will reduce the condensation load. Reduce the condensation load at the top zone. The third one, when the vapor was condensed from the heat mixing in the above tray, the vapor flow rate will be reduced. In this case, when the vapor flow rate is reduced throughout the column diameter can be don't need to be that big. This is also some calculation showing up here. For example, on stream A, which has the crude of 1000 pound per hour with the CP over is equal to 0.7 BTU per pound degree Fahrenheit. And then we would like to reduce the temperature of 500 degree Fahrenheit to 400 degree Fahrenheit by passing that to the PA heat exchanger network and to preheat the crude oil of 200 degrees Fahrenheit. So we can calculate that the mass of crude oil that should be passed to this based on 100% heat transfer coefficient is around 1400 pounds per hour. So in this case, about 70k BTU per hour can be removed from the column. So we can utilize this heat for the preheating of the crude oil instead. Okay, about this slide, it is about what benefits we will get from the PA or pump around heat removal. The first one, if we don't remove the heat by the PA, temperature at the top will be higher than 265 degrees Fahrenheit. Well, that will cause more duty to remove the heat out here, otherwise the energy may be lost. The second, for the higher temperature to 140 degrees Fahrenheit, some deposition of the calcium chloride or magnesium chloride will be show up in the tube, as we mentioned before. So we better keep the temperature down lower than 125 degrees Celsius in the condenser here. And if the more vapor show up here, and after the condensation, it will be a lot of liquid product on the top tray, which may cause flooding in the top zone here. Consequently, on the fourth benefit of using pump around, the flooding will build up the pressure drop. If you have the more liquid coming in here, you will have the flooding. It means more liquid on each tray and no vapor can be moved up. When the flooding is built up, and the flooding will build up the pressure drop, which we don't want that to be happened. Now we come to the last slide, vacuum distillation unit. The vacuum distillation unit requires a system to create the vacuum down to 20 to 50 millimeter of mercury. In general, either ejectors or a combination of ejectors and vacuum pumps can be used. But in this figure, you will see only ejector that present here. This is a symbol of ejector. Ejector will compress the gas through a nozzle where vapor from the column are sucked into the venturi section. So it means there is a stream coming in, and then with a very high velocity, they will suck the vapor or liquid after condense to this area and then condense to the products. Coming up with this slide, You will see the detail of using ejectors by the YouTube that I already attached to this clip. And also we would like to mention about the products comes out from vacuum distillation unit. There are three groups. One is light vacuum gas oil, which may go directly to gas oil pool. The second one is a group of middle vacuum gas oil and heavy vacuum gas oil, which may generally send to hydro trading before going to the FCC fluidized catalytic cracking or some cracking process. And then the last one, the one in the bottom here, we call as the vacuum residue, which will send to break down the viscosity or to produce some other coke. Thank you for watching, and then see you in the class. Thank you.